So then let's get started. We continue our lectures on data science for business. Topic for today's lecture is personalization and recommender systems. Okay. All right, give me 1 second. All right, so what do we understand when we say personalization? Well, personalization really means is delivering the right experience to the right customer at the right time. And in fact, all of those three words are extremely important, because even sending the right message in the wrong time is not going to work. Think about those phone calls that you get at random time from banks or other services that will try to advertise, right? Dental services. Now advertising in Moscow a lot. So it's the right experience, which means it's a product recommendation, or it is a particular reward or certain content that's being delivered. It's the right channel, and a channel means either through the web or through mobile or maybe email or push notification or in person, and at the right time. The time when you're really ready to accept the discussion, and the time that is relevant, right? For example, advertising umbrellas when it's raining outside is actually a pretty good idea, and it's probably not such a great idea, in the middle of the summer. So personalization is extremely effective, and that's why a lot of consumer good companies really want to do it. And of course, all the services like financial or telecoms, they're also big fans of personalization. So if you notice, these are just examples from the BCG report on personalization in retail, where it looks like that based on the respondents survey, the number of items purchased based on personalized recommendation can actually almost double, right? And the value of the average order increases, and the overall net promoter score is growing. To build the technology, to build the personalization, to make the offer personal, we need to know the customer, right? And knowing the customer could be, as we discussed previously, knowing, for example, information about where the customer live, maybe gender, age, etc. But at the same time, some sort of personal information. But at the same time, you can also base personalization of the behavioral information, and personal information not always available, but behavioral information can be and often are collected. For example, all those the valued membership cards that you're getting, right? They really given to you to collect information about your purchases, right? And later on do the personalization based on that. And of course, there are a lot of technical things, technical challenges you need to overcome to make this work, starting from data management, data collection, to building analytics engines, to adding this personalization layer, and finally actually delivering it to the customer in the right place, in the right time, and the right way. And in fact, of course, the pioneers of this personalization service were online companies like Amazon, and the reason for that is because all the data has been easily available, and for traditional brick and mortar stores, it took some time to, well, first of all, get online, but also to be able to merge the information from online store, online purchases, and sort of real physical stores. But nowadays, it actually, for a lot of retailers, it works pretty well. So we're going to look today at the two techniques. First technique, which is actually quite general, and it is, I would say, precursor to personalization, is called market basket analysis. And this is quite simple and straightforward statistics that is based on the items that customers purchase together. So this is not personalization in the sense that we are not here building personal profile. What we're doing is we're looking across all the customers, all the purchases. So actually there is no sort of customer in here. There are purchases, there are baskets, and we look what kind of items occur in the baskets. Occur meaning, purchased together. And from that, we're trying to build association rules, which is really the rule like if then statement. So for example, if customer has purchased item A, then it will with high probability purchase item B, right? From A follows B. So that will allow, that knowledge will allow to do well, cross-selling on the items, which means, if somebody purchased one item, can be recommended some other item. And then, for example, product store placement, right? Placing next to each other items that quite often purchase together. And by doing so, you kind of motivate customer to remember they might need that item. I mean, like, I don't know, obvious beer and chips, right? And affinity promotion, which is, well, promoting one type of promoting one item, you might actually either promote the other item that is purchased usually together with this item, or other way around. And so typically what you need to build market basket analysis and later on personalization system is point of sale data, sort of transaction data, where we have usually transaction number, which is sort of unique identifier for the purchase. And then there might be items like here it shows there are two SKUs for latte and muffin, and they both correspond to the same obviously the same store number and the same transaction number. In fact, the data that I have shown here in this example is a bit richer than what we need for simple market basket analysis. So here, if you look at the first column, you see that there is also a card number, right? And so here we can associate every purchase with a particular customer. And by doing so, we can later on build an assembled personalization engine for particularly designed for that customer. At the same time, if we just want to do market basket analysis, we do not need information on a particular customer, so who actually made the purchase, right? And in fact, that information only available when there is a card number, loyalty card, and if there is no loyalty card, well, there is no such information available. Okay, so how do we build those association rules? Well, the idea is to analyze the frequency of purchases, the frequency of the occurrence of various purchases. So in order to do this, we introduce two metrics. One metric is called support, and that's really frequency of the item set in the data. And then based on that, we can calculate confidence and lift. Confidence is measured by it's proportional to the conditional probability of event Y given the event X, and you can instantly interpret it as the probability of purchasing Y given X, and X can be one item, two items, whatever. And lift is actually how much the presence of one item affect the presence of another. This is lift is, for example, if you look at the probabilities, if the purchase of two items are independent, then mutual probability, joint probability of purchasing two items, P of X, Y, factors out into P of X and P of Y, they cancel out, and so the lift is equal to 1. So lift is 1 if the purchase of one item does not affect the purchase of another item, and if the purchase of one item affects it, lift is greater than 1. So here on the right hand side, there is an example database with 5 transactions, 5 items. And so if I look, for example, at the first row, give me 1 second, turn on annotation. Right. If I look at, for example, the sort of the difference row, different rows. Let's say I look at the column, say butter. The support is relative frequency of the purchases, right? And so butter here has been purchased twice, here and here, right? Out of 5 transactions. So support is 2/5, 4.4. So it's 40% chance that someone just purchases butter. If you think about this as the entire world of purchases. If we think about milk and bread, well, as sort of X, then milk and bread together has been purchased twice, right? There are 2 transactions where milk and bread both are present, and so it's also 2/5, also 40% chance that they're both purchased together. Now, then the question is, okay, how about if all 3 of them, milk, bread, and butter, purchased together? It should be here, comma. Well, for 3 of the items to be purchased together, there's only one such an event. It's right here. There's this transaction when all 3 purchased together. So it is 1 out of 5. So it's like 20% chance that they 3 purchased together. And then based on that, by the rules of probability, we can actually calculate, for example, what's the probability or likelihood that if somebody purchased milk and bread, that they purchase butter, right? So it's P of Y given X. We can calculate that, and this is, just literally following the rules of probability. Probability of both of 3 items purchased, all of them purchased is 0.2. We just calculated it here. Well, so this 0.2 and divided by 0.4, which is a probability of just a pair. And so there's this 50%. So confidence is 50% of the rule or conditional probability that given that somebody purchased milk and bread, they will purchase butter. It's actually a 50% chance. And so, we can recalculate this as a lift. And so lift is 125. So it actually tells us, yes, if somebody has milk and bread, there's a good chance, they have butter in. And so, you can actually use that information to place butter next to milk and bread, for example, in the store, or if somebody at the checkout or online has purchased those 2 items, well, you know what to suggest, right? Now, this is an easy exercise, really just counting, right? Counting and normalizing. But unfortunately, it's not that easy when you have millions and millions of transactions. And in fact, remember, these are transactional data, right? So it's not the unique customers, it's transactions. So there is actually a special algorithm, which is called association rule, which is called, a priori algorithm. It's quite famous. It allows you to calculate to build those association rules on a large, very large data sets. So that's actually, what we really need. And the way it works is the following way. I'll just sort of outline the idea. The idea is through all the item sets, select what's called frequent item set. And frequent item sets are those whose support is greater than some minimum number. And just to remind you, support is really the frequency of the item set in the data. So it is, just sort of, we can select the one that has support greater than, some number. Well, we can, for example, say in this example, let's look at the and the frequent item sets with a support greater than 2. So how do we do this? Well, it's actually quite straightforward, but you need to think about it that way in order to work on the very large data sets. So the idea is the following. Let's say we have here transaction IDs, and there are 4 transactions, and the first transaction there is items A, C, and D has been purchased, and here is B, C, and E been purchased, etc., etc. Right? A, B, C, E. Somehow Spotlight doesn't really do what I want it to do. Okay, so then we can literally just go through this numbers and calculate how many times, for example, the item A occurred overall in transactions, and there are two times, then item B 3 times, item C 3 times, item E 3 times. So the idea is that if you look for frequent item sets, a subset of the frequent item set also must be frequent. So what it means, if we're looking, so because of that, we can kind of go bottom up and start cutting out subsets that are infrequent. So for example, if D occurred only once as a sort of single item, it cannot occur more than once, within 2 or 3 items sets. And so then we can just eliminate D at the very beginning, right? And that's what we do. So for example, here, again, if we're looking for example, minimum setup is 2 items. So first we look at the single item setup, single items, and just count how often they occur in the database. And then we just count those numbers. That's the support. We cut out those items that have very low support, so they're very infrequent. Then we have this item set, and we go through this item set and form all the possible pairs in this item set, which is going to be A, B, A, C, B, C, B, etc. And calculate the support. So how often they occur together, for example, item set AC, right? How often they occur in the database. And here it's 2 times, 2 times, and BE happens 3 times, right? It happens here, it happens here, it happens here. All right. Actually, I jumped through this slide. So, we formed from item set, we formed pairs, then we calculated the frequency of pairs as I showed. And for example, AB occurs only once, AE occurs only once, so we'll drop them. And then eventually what we get is, because only we have AC, BC, BC, we can only have 2 combinations of 3 letters. It is BCE and ABC, and actually ABE. We can calculate, then check how often they occur, realize that ABC occurs once here, ABC, ABE also occur only once in here, and then BCE occurs there, and the second time here occurs twice. So that's our item set that is most frequent, and that's how you calculate support for sort of the purchase of 30 items. And then you can keep going if you want to, but typically, people not interested in sort of in a much larger sort of, it's not practical to look at the much larger basket analysis. So it's usually 2, 3, maybe 4 items. That's done in practice. So that is a traditional technique, right? Has been used for a long time. It's called association rules mining. And this technique is a precursor to the actual personalization, but it does allows us to, help to do a cross-sell, to extend the customer basket. Okay, any questions on association rules? All right, moving ahead. So recommender systems. So the next step in this sort of in personalization is recommender systems, and they were pioneered by Amazon, and they were pioneered by Amazon in really sort of late 90s. And after that, of course, today, like all the major online services, they do use personalization. It is that it is for items you purchase. It is for new songs for you to listen to. It's movies to watch. So Netflix is famous for setting up a competition a while ago with a $1 million prize to beat their own algorithm, personalization algorithms. But it all started back in the 90s at Amazon. Now, why do we need personalization, and why it became so important in the era at the time of online sales? Well, the fundamental difference in between sort of online store and traditional sort of store in the mall, brick and mortar store, is that traditional store has a very small assortment that it can keep in the store. Well, relatively small, and that's because, well, the store areas, the store size is not very large usually. Plus, you need to keep it supplied somewhere, etc., etc. So, because of that, in traditional stores, the stores, they keep most popular items, right? They keep in store most popular sizes and most popular items. And so in some sense, they work on this side. Oops. They work on the left side of the curve. If we'll drive sort of popularity versus products, you can have a curve. This curve is a power law curve, which means it drops very fast but has a very long tail, which really means that there is some number of items that are extremely popular, but the majority of items are not that popular, but there are lots and lots of them. And Amazon, for example, if you think about, actually step back one step, if you think about, say, retailer, I don't know how many jeans are out there. Well, there are some number of brands of jeans you can sell, but they're not very large. But if you think about how many books are out there in the world, well, that's huge numbers. And of course, bookstores don't keep all those books. They keep only the most popular books. And Amazon, since it was their mail order, it could have in their warehouses lots and lots and lots of different books, maybe not very popular, maybe in a very small numbers, but there's this sort of huge tail, long tail of items available for purchase. And then when you have long tail of items available for purchase, the question becomes of discovery among those items and recommendation of something that is not just the most popular, right? Because the most popular recommendation is obvious, yeah, right? Look for the highest frequency requests and recommend it. But that's of course, Amazon can do it, but the power comes not from here. The power comes from here, from the long tail, from the usage of recommendation on the long tail, for recommending some sort of obscure movie that you might like, you never heard about, and might not be very popular among other people, but it might be interesting to you, and yes, you will pay money to watch it, and that's the whole point. And though it looks like this side, number one, is if you think about the popularity and number of products, right, the area under the curve is, let's say, the proxy to the total amount of product sold. It looks like one is this blue area is much larger, but in fact, due to the fact that this tail is really, really long, eventually, the area under this long tail actually becomes larger than the area, the number of popular items sold. And that's sort of what makes the business of Amazon and in general online stores so successful. So, but in order for this to work, in order for customers to being able to discover items in the long tail, they first of all need a very good search engine. But the other thing is they do need to have a very good recommender system. So customers will discover something they really don't know yet, right? So it's really should be discovery. Search is not really discovery. Search, you put in the query precisely what you're looking for, and here we're looking for sort of some unexpected result. So recommendation engines. There are really sort of two ways to think about this. You know, the overall the technique we're going to talk about today is called collaborative filtering because it's based on collaborative information, which means based on information of the purchases done by all kind of customers. You can also talk about sort of content-based modeling, where you look into the content, sort of into the content of the items, which is you can think about you know, names or titles or synopsis of the books, etc., or movies. Now, the overall idea of collaborative filtering is that you either look for similar, so you look for similar users, and similarity between users can be calculated through their behavior. For example, if both users watched the same movie and rated them highly, then you might assume, if it is one movie, okay, maybe it's accidental, but let's say if they rated 3 movies, both of the people independently rated 3 movies highly, well, they probably have somewhat similar taste. And then if there is a movie that one person liked but the other one hasn't seen, well, you can recommend that movie to the person who hasn't seen it, or the book or any item. When we talk about content-based, here we need to define similarity between items, and if somebody purchased an item, then we can offer similar item to a person, and similarity can be calculated again based on the content, but in fact it can also be calculated through collaboration. I'll talk about it in a second on the second slide. When similarity is calculated through the collaboration, it's called often item-item collaborative filtering, and when you do through the users, it's quite often user-user collaborative filtering. And on the right-hand side, you see this industry report from Amazon.com. I can't see it right now on my screen, but it's probably, I think it's sort of maybe year 2000 or late 90s. And sort of this is a paper that sort of started the entire field of collaborating filtering. So how does it work? Well, it's the easiest way to understand the mechanics behind collaborative filtering is through looking at it as on a graph. So let's look on the left side. Here I show you a bipartite graph, right? The bipartite graph is a graph that consists of 2 types of nodes, and in this case, one type of node are people, users. Another type of node are items, books, and the idea is that, okay, the user can purchase an item, so user purchases a book, user purchases a book, user purchases a book. So here is, 3 arrows or 3 edges in this graph. So then we can, redraw this graph sort of in this abstract way. There are users A, B, C, D, E, and there are items. And notice here that, for example, if we look at the user A and user B, then we have user A purchased, say, item 1, purchased item 2, and purchased item 3, and user B purchased item 1 also, item 2, right, and item 3. So in this sense, the users 1 and B, they're very similar because out of 4 items, each of them purchased the same 3. And then if you think about collaboration, going forward, well, you can say, okay, well, there is this item number 4 that user B purchased. Well, maybe we should recommend it to user A. And that's kind of the essence. Now, to make it work, what you can do is you can by taking this, you can take this user item bipartite graph and actually create projections of this graph. You can either project it on users or project it on items. Projecting it on users means creating only a user graph, so where the nodes are only users. Projecting on items is creating a graph where nodes are only items. And the way they're connected is the following. If there is a connection, two-step connection between node A and node B, right? So two-step, which means I go one way to, right, two-step connection. Then there is an edge between those two nodes in this user projection graph. So user. And then if there's here, there is like 3 ways to actually go from node A to node B. So the value here is going to be 3. Or node B and D, well, they're connected through 2 steps, go from B to 4, from 4 to D. But that's only one way you can get there, so it's weight 1. The interpretation would be, okay, nodes A and B have 3 items in common, right? Node A and B has 3 neighbors, 3 common neighbors. If you think about this graph as a traditional graph, so items A and B have, users A and B have 3 common neighbors, and users B and D have 1 common neighbor, and users say C and E do not have any common neighbors, so there is nothing here, there is no connection. And yes, there's no connection here in the graph between C and E. All right, so this is user projection graph, user graph, and the same idea, you can also build an item projection graph. Here is there is a connection between 2 items if they have been purchased together, or I'm sorry, if there are enough users that purchase them. For example, item 1 and 4 has been purchased together by one user B, and so there's this weight 1. Items 1 and 3, so 1 and 3 has been purchased together by 2 users. So user B purchased item 1 and 3, and user A actually purchased item 1 and 3. And so that's why there is a weight 2. And so by doing this, we can create user and item graphs. And now the meaning of this graph is really a user, for example, user projection graph is a user similarity graph. It's how user A is similar to user B, because they have 3 items in common that they purchased. So they're quite similar. Users B and D purchased 1 item in common. So, they're not really similar, but maybe there's some similarity among them. Users C and E, not connected here. They never purchased any items of the same type. So they're not similar at all in the way we understand things. And the same type of interpretation can go for item graphs. Here, item 1 and 3 often purchased together, often purchased by the same customer, so they're similar in a sense. Okay, and you can think about items. So we can talk about here, the ratings for the movies. It all follows the same logic. Now, how do we actually use this? Well, the way to use it, if we have, for example, a user-based, it's called user-based top-end recommender system. So it is user-based because we, for every user, we find users that are similar to the user. And then it's top-end, I'll explain in a second. So let's say we have this user projection graph. We selected one particular user, and let's say it's well, user, yeah, it says here user A. Okay, fine. We selected user A. User A only have say 1 user in common, which is user C. But if we selected, say, user B, then it has 1, 2, 3, 4 other users, similar users with the weights on edges, right? So we select those users. Then for each of those users, we can look at what items they have purchased, right? Because we have that information in the original graph. And then we can count how many items of each type has been purchased by those users. Sort of this is 4 times they purchase this t-shirt and 3 times gloves, etc., etc. And this is a list, this is a ranked list that can be proposed to user A for purchases. So it's called collaborative because it is based on collaborative actions or actions done by all the clients. It is top N, well, because we select top N users, the most similar users to your user, and pick up their purchases and sort them. And so this is user-based top N recommender system. Alternatively, you can have item-based top N recommender system. This works slightly different, but quite similar. So the idea is you have a user, and let's say user purchased, say, 2 types of items, purchased the shirt and the gloves. And then what we do is we go into the graph. Now it's item graph or item projection graph. We take one of the items, let's say it is the shirt. We select similar items to that item and show them. Then we take another item the person purchased, we select similar items to that item, and then the same way we count the most frequent and select them. Well, here we got just 2. What in fact we should have all 4, but here there is pretty much each item's purchased only once. Now we don't have any 4 here simply because user already purchased shirt, though glove is similar to the shirt. We should remove it and not show in the final results. And since gloves here, but the user already purchased them, we also throw them away and not showing the final results. So this is a final sort of suggestion, recommendation to the user. In fact, item system typically in practice works better. It's sort of item-based top N recommender system or item system. This is what Amazon actually put in production back in 2000, and that what became extremely powerful and make Amazon eventually so rich, right? Amazon is famous for its recommendation. Well, and now Netflix also. Right, so here a quick summary for this matrix graph representation. Yes, we'll look at the matrices. We actually, instead of talking graphs, we can talk matrices, right? So whenever you have a graph, you can represent the matrix. If the graph is unweighted, it's a binary matrix. If graph is weighted, it's also a weighted matrix. So the matrix with weights in it. And if it is bipartite graph, with bipartite graph, you can actually represent it also as a matrix, but this time the matrix is, looks usually like a table where you have, for example, rows that corresponds to one type of items and columns to another type of item. So it's not adjacency matrix, it's slightly different matrix, but it also can be presented as a matrix. So whenever we talk about graphs, the alternative representation are matrices. And the reason I'm talking about is because so far, when we discussed the approach, collaborative filtering approach, we talked about a graph representation, right? We worked with graph. Now, if we look at this slide, in fact, what we're doing is for let me draw it. If we have this user item graph, what we're actually trying to do is we're trying to predict which item user is going to purchase next, right? Which item they're going to like. And that really is what we're trying to do, is we're trying to kind of add or predict the new edge, right? The new edge in the graph, connecting users, for example, and items. And in fact, if we also look at the similarity graph, so if we look at if we not just looking at the binary relations, but saying, okay, our edge should carry some weight depending on the strength of our belief that, for example, user one is going to purchase item C, or for example, if C is a movie, that the user will rank it highly. We can also try to predict the values, right? So not only binary 0 and 1s, but the value. And the thing is, literally, there's a sort of zeros, and what we're trying to do is predict what values could be there, so that the user can purchase, right? So predicting new items to purchase for a user is really predicting existence of the link in the future, appearance of the link in the graph. And the link in the graph means replacing 0 in the matrix with some non-zero value. Now, the reason I'm talking about this mathematics is because there is a way to actually predict those user rating, to look at it through the matrix formation. Again, if you look right now on the left-hand side, when we see the matrix original bipartite graph, there are users and there are books. And for example, these are the ratings users gave to the books. And you notice in some places, for example, the first user rated these 3 books, right? The other users say this user rated this book and that book. Everywhere else, there are empty cells, but empty cells means that user never read the book, and so the goal of recommender system would be to fill in those empty spaces. And as we discussed, we could actually do 2 things. We can either get sort of user graph, and this is that graph but shown as a matrix, and with the weights calculated from this grades. And then we can also do sort of item similarity graph, also based on this mutual purchases, right? The way we have described. And then based on that, we can literally, calculate for user, for each user, we can calculate sort of recommendations, right? So this, excuse me, this excuse me, guys. Okay, so this is pretty much the same as what we talked about for graphs, right? But this is expressed in terms of the matrices. But now, if we looking at the matrices, there might be, more type of interpretation. And if we look at this matrix, for example, we can interpret similarity between, for example, items using so-called cosine similarity, just by thinking about items as, say, vectors, and then doing a cosine similarity by multiplying those 2 vectors and looking for an angle between them. And we do multiplication only, of course, for those parts of the vector, for those coordinates that do exist.
And can we combine these features with psychographic features? For example, if we someone like Ozone and have access to consumers' profiles in social network such as Vkontakte. So, for example, if we scrape their profiles and analyze their interests, so do you think it would be a good idea to combine their data from site, for example, Ozon, and Vkontakte psychographics?
Right. In fact, that's pretty much what every big company is trying to do, is trying to enrich data as much as possible, right? Use the behavioral data and enrich it with sort of demographic data or any other data that is possible. Now, there are some sort of legal implications for doing this, but technically, yes, that's what people trying to do. Within this very simple framework, you probably can use this secondary information maybe to reorder the items that you get based on this collaborative filtering, or maybe you can sort of add this information directly to the graph. So there might be sort of various ways of doing so, but yes, absolutely, technically this can help. All right, guys, and last thing, but not least, is sort of what I have described to you, this recommendation system based on collaborative filtering, right? That recommendation system is really sort of, again, late 90s, early 2000s, that's when it kind of was introduced and used, and later on, by sort of looking at this graphs and looking at it through the matrix angle point of view, it became clear that one can actually think about this through what's called matrix factorization. So one of the most popular ways of doing this is through singular value decomposition, which is, it's a linear algebra technique that allows you to sort of split matrix into the product of three matrices and then sort of reassemble it back. Now, why would you want to do this? Well, in fact, by doing so, it allows you to fill in those empty spots with some sort of predictions. And there are a lot of literature out there that sort of discuss why this might work and how it works. But in sort of few words, sort of generally speaking, the idea is that you can, by doing this kind of decomposition, and here it's again, it's the simplest decomposition that is possible. We actually introducing, say, some multi-dimensional space. It's usually called latent space because we do not observe it. And we represent users and items in that space. And so users, so there's some sort of space. Here it's shown as a two-dimensionals, and users becoming vectors in that space, and items becoming vectors in that latent space. And then similarity between users and items, calculated through traditional dot product. And then we can have sort of, in different places, here is going to be a sort of a vector for the user, and in the same space, there is a vector for some item or that item, that movie, and then the angle between them is small, so the dot product is small, and so the user will like that item. Or for example, this user and this item are at 90 degrees almost, the dot product will be 0, this user will never like that item. So here it's called matrix factorization. The more modern name for this technique is embeddings. So by sort of you taking the information and embed it in some low dimensional space where users and items are presented as vectors, and the way this embedding is done, either through various matrix factorization techniques or today through deep neural networks. And this is sort of more advanced way of doing things compared to traditional collaborative filtering. It allows you to sort of improve the quality of results. But again, in many cases, sort of traditional collaborative filtering gives you this sort of 80% of the accuracy. Of course, if you have millions of people sort of basis, of course, every sort of every percent point counts, and that's why Netflix, for example, announced that computation in mid 2000, offering $1 million for improvement over their current prediction algorithm by, I think, several percent. We should have improved to win the competition. And in fact, the competition was won by the team that proposed the matrix factorization technique, certain type of matrix factorization. Now, one last thing is, of course, recommender system. They are a part of sort of traditional, the part of machine learning, and you can also do sort of and train, test, split, and measure quality for this systems. So when you do train and test, the differences in traditional ML would probably just split. We typically split by items. You have your rows of your matrix and you do the split. Here, when we do recommender system, we need to be somewhat smarter in terms of train, test, splitting, because here in our sort of data matrix, we have users and we have items users purchases, and you do not want to completely throw away users, and you don't want to completely throw away items, right? So if you split just by user side, you might lose all information about any user. And so that's why when you do the split for recommender system, it's usually done by subsetting, so selecting, keeping all the users and all the items, but just removing some of them randomly, sort of some items for some users, and not the entire sort of user with all the items the user purchased, and not the entire sort of item with all the users who purchased it. And then you calculate quality metrics. Now, of course, you can calculate traditional root mean square error, but that might not be appropriate here. In recommender system, we often calculate the quality the same way as in information retrieval, by introducing two metrics. One metric is called precision and another called recall. And we talked about the quality of classifiers, and over there we introduced false positive rate, true positive rates, etc. Now this is similar, but the difference is that precision and recall do not take into account sort of negative events, or do not use irrelevant documents per se, or irrelevant items. So the notion is the following: precision is calculated as the number of relevant documents among retrieved documents. Think about search engine. In a search engine, you make a search query, you retrieve some number of documents, let's say first page, and you calculate how many relevant to you search results are on the first page, right? And the same thing with recommender system. You get a set of recommendations and you calculate how many of those recommendations are relevant to the user, or you can even just sort of rank relevant them. And recall is really the ability of the algorithm to pick up all relevant documents. So again, here we're looking at the relevant retrieved documents, but finding the ratio with all the relevant documents. So if you look at the number of relevant documents that you returned by the search engine, you find the ratio of that number to all number of relevant documents that you might know that exist out there in the world. Now, typically, recall is not very easy to compute because you need to know, the total number of relevant to you documents out there. and that might not be available, but precision is always computable. Precision is really the purity of the results you get. And we're always trying to get high precision, high recall, right? Again, precision means the purity of the set you get. Recall means the completeness of the set, right? That all the documents if you picked up all the documents from out there. And so, when we do a recommender system, we quite often use precision and recall as metrics instead of true positive, false positive rates, though those metrics are related. So finally, to sum up, with recommender systems, there are really already 3 generations of this recommender system. So the first generation is the one that sort of goes back to early 2000, which is Amazon-based systems, where you're talking about collaborative filtering, the one we discussed today in detail. And there can be content-based, so we're looking at the content, knowledge-based, so maybe there's some historical or some knowledge that you want to put into the system. Now, the second generation system is mid-2000. This is matrix factorization. This is a way to look also at this user item matrices, but instead of just doing this simple collaborative filtering and looking sort of for nearest neighbors, we look at this as a matrix, and we try to fill in gaps in the matrix through some sort of interpolation, extrapolation techniques, by projecting it into this low-dimensional space, looking for embeddings. This is what's called matrix factorization, and those are techniques that has been pioneered and used a lot by Netflix. And now today we're sort of on this third generation of techniques, which are based on deep learning methods, sort of deep neural networks. But the fact is those methods, they also look for certain type of embeddings of items in this low dimensional space, but on top of sort of mutuality of the purchases, they also can encode the sequence of the purchases, and sort of the time frame of the purchases, so that the recommender system becomes time sensitive, and the items purchased more recently play a higher role in recommendations than the items purchased earlier, right, in the history. And of course, there are other sort of ways to enrich the recommender system, like you actually asked, by bringing in information from social network or other sources. And finally, here is quick comparison, right? Amazon actually gives you, when it provides recommendation, it gives you this frequently bought together thing, right, as a recommendation, and you can actually add both, right? And so that's based on the market basket analysis. And then a customer who bought this item also bought other items. That's precisely collaborative filtering that sort of is for you finding similar customers, right, to you, and then suggesting other items. And if you want to learn more about it, there's a great book. It's also available online for free. There is a newer version, new edition of this book, Mining of Massive Data Set. There are a couple chapters. I think there's a chapter there that is dedicated to recommender systems. Okay, and with that, we are done for today. Any questions, please? All right, so if there's no questions, we are all done, and later on there will be a seminar as usual. All right, guys, thank you very much.
Thank you. Bye.
Thank you. Goodbye.
Bye-bye now.
Bye.